Bismillahirrahmanirrahim. Welcome to the new lecture of data communication networking. It's the second part of chapter number 10. So today we are going to study about the Hamming distance. So the Hamming distance between the two words is the number of differences between the corresponding bits. So what does it mean? I will show you by an example, but just keep in mind we will use XOR operation. With operation we need to be use XOR operation. Okay, coming to the Hamming distance now. Like example 10.4, let us find the Hamming distance between the two pair of words. So we have two pairs. The Hamming distance is 0, 0, 0 and 0, 1, 1 is 2, because let's see now 0, 0, 0 is a one word and 0, 1, 1 is another word. So now you can add it by XOR operation. Hope you guys know about XOR operation. So it will be 1, it will be 1. Okay, so how many ones we have? 1 and 2. So this is 2 bit. So what is the Hamming distance? The Hamming distance is 2 now. So if you can see, the Hamming distance is 2. Let's come to another. The Hamming distance between 1, 0, 1, 0, 1 and 1, 1, 1, 1, 0 is 3. How is it? Now you can see. Let's say 1 and 0, the result will be 1. Then 0 and 1, the result, so 0 and 1, the result will be 1. Then 1, 1 will result will be 0. Then 0, 1, the result will be 1, and 1, 1 is 0. So how many ones we have now after XOR operations? So 1, 1, 1, so 3 ones. So what should be the Hamming distance now? The Hamming distance will be 3. Okay, this is simple method how you can find the Hamming distance. So the minimum Hamming distance is the smallest Hamming distance between all possible pair in a set of words. Okay, so what is the minimum distance between two? So this is the minimum, because 2 is the Hamming distance, and here is a 3. Okay, so coming to another example 10.5, find the minimum Hamming distance of a coding scheme in a table 10.1. okay, let's see here we have a 0, 0, 0, 0, 1, 1. What should be the Hamming distance? How many ones we have? 2. So 0, 0, it will be 2. So then how many will be? It will be 2 Hamming distance. If you can see this, making a XOR operation, the 2, 2, making it XOR operation 2, 2. So how much is the minimum Hamming distance here? The minimum Hamming distance in this case is 2. So example 10.6, find the minimum Hamming distance of the coding stream in table 10.2. like this is, now you can make X operation. So 1, it will be 1, 1. So how many ones we have? 1, 2, 3. After XOR operation we will have a 3 ones. So the Hamming distance will be 3. Make a XOR operation of this, the Hamming distance will be 3. Make XOR operation of this, the Hamming distance is 4, Hamming distance is 3. So now what we need the minimum Hamming distance. So let us find out the minimum Hamming distance. 3, 4. So what is the 3 is the minimum Hamming distance. Okay, so to guarantee the detection of up to S error in all cases, the minimum Hamming distance in a block code must be D minimum is equal to S plus 1. S plus 1, what does it mean? S is your number of a bit error, number of your corrupted error, how many error are corrupted. So S is called, and plus 1 is just like 1 bit error correction. Okay, so this is D minimum is equal to S plus 1. Okay, and keep in mind Hamming distance is basically we use that when we have a bit error in a code word. So we just try to find it out, because we have a sender side and we have a receiver side. In a sender side we have a code word, in a receiver side the receiver receives the code word. So make the comparison between each other according to XOR operation. If there is a number of a 1, so it means there is a error. If there is no one, let's see like this, 1, 1, 1. This is your sender, and let's see this is your receiver. Receiver receive this one, so 0, 0, 0. So sender send this one, receiver receive this one. So one they are making an XOR operation, so result is 0. So it means there is a no bit error. Okay, but if we can use like this is 1, sender is sending a 1, 1, 1, it's going to be sent, and the receiver receives 0 1 1. So after XOR operation it can be 0, it can be 0, it can be 1. So how many ones we have? 1. So it means there is a bit error now. Okay, so there is a bit error, so receiver know, oh, the error is detected, so then we need to be correct the error by another method. Okay, so coming to the geometric view of this, let's see, we have a circle or a code where we have a number of bits, and we just make a center of this one and make a radius based on number of bits as radius as. So how, what should be your d minimum? So keep in mind d minimum is always greater than s, because we add plus 1 with it, so that's why d minimum is always greater than number of s. Okay, so legend all valid code word, any black will show or any valid code word, then the dot dot shows any corrupted code word with 0 to s error. Okay, so this for your information that how this is your code word, it's going to be signed by, this is your corrupted code word which will be stay there, we need to be corrected out and then use it. Okay, then coming to another one, once we have a two territory of x and territory of y, so again this sign show that any valid code words, and this will show the corrupted. So we have a two, so to guarantee correction of up to t errors, because we have a two code words, so it will be 2t, so the minimum Hamming distance in a block code must be d minimum is equal to 2t plus 1. 2t is your number of bit error and plus 1 is the number of bit correction. Okay, so again this is about just a formula where we use it out. So in example later on we will see how we can use it out. So now example 10.9, a code stream has a minimum Hamming distance d minimum is equal to 4. What is the error detection and correction capabilities of this? So if you say d minimum, he's saying this is 4, and according to formula we have s plus 1, so how many bit error will be? 3 plus 1 is 4, so 3 is a bit error and what is the correction? So that this code guarantee the detection of up to 3 errors, because 3 plus 1 4, so 3 is your bit error, 3 error, but in it can correct up to 1 error, in other words, if this code is used for error correction, part of its capability is wasted. Error correction code need to have an odd minimum distance 3 5 7 9 and so on. I will tell you what is about odd minimum distance, because in error detection in error correction we will study about. So coming to the linear block code, so almost all block code used today belongs to a subset called a linear block code. A linear block code is a code in which the exclusive or addition module 2 of two valid codes create another valid code. It means that when we have a two code words, when we make a XOR of a two code, it will give you a third code word. So I will tell you how it will work. So the topic discussed in this section will be minimum distance for a linear block code and some linear block codes. So in a linear block code, the exclusive or of any two valid code words creates another valid code word. So what does it mean? Let's see. According to this example, we can easily be. Example 10.10. Let us F2 code we define in table 10.1. I will show you table 10.1 and table 10.2 belong to the class of a linear block code. So let's see, for example, the stream in the table 10.12 I will show you in a linear block code, because the result of XORing any code word with any other code word is a valid code word. For example, the XORing of the second and a third code word create the fourth one. Now I will show you. Let's see, this is your table 10.1. we have a two collates and code word of 2 and 3. When we make XOR of these two ones, so 1 1 will be 0 1 1 and 0 1. So this is your third code word now after XOR operation. So basically in this he's saying that when two code words are going to be XOR, the resultant will be your next code word. Okay, the stream in table 10.2 is also a linear block code. We can create all 4 code words by XORing 2 other codes. Okay, so if I can show you, the table 10.2. So if you can see table 10.2, let's see the code word of second and third. So then it will be the next. So 110 101 01 101 01. So this is your XOR operation, and this is your next code word in table 10.2. Hope this will help you. So now coming to a simple parity check code. A simple parity check code is a single bit error detection. Just keep in a single bit error detection in a simple parity check code, in which so n is equal to k plus 1. So what does it mean? N is equal to k plus 1 mean that your code will be k will be your message plus 1. Plus 1 mean you can add one extra bit. So it can be also be known like 1 bit error correction as well. But here it shows that n is equal to k plus 1 mean n is k is your message and plus 1 add 1 bit. Okay. So and what should be your minimum distance? D minimum will always be 2. Because why D minimum? Because if you remember the formula, it was s plus 1. So there is a 1 bit error. Okay. So 1 bit error, so plus 1, it will be minimum distance of it, having distance will be 2. Okay. So we have a two concepts as I mentioned before as well, even parity and odd parity. In even parity means that number of one in a code will be even, or in odd parity it shows that number of one in a code word will be odd. So let's see, I'm showing here. Let's see simple parity check code. See with the 5 and 4. So 5 is your code word and 4 is your message. Then how many bit we need to be add here? How many extra or redundant bit we need to be add here? 1, because 5 4 is equal to 1. So this is your data word now. So data word, this is your 000, and code word we need odd, we need a even parity. We are talking about even parity. So one extra bit we are going to be add, it will be 0. It show your even parity. So coming to this one 0001, so we need to add one extra bit, and but we are talking about even parity. So the next bit once we are adding, it will be 1, because it shows it make a even parity. Like this one, this is 0010. So we add one extra bit with it, but we are taking a even parity. So 00101. So and so on, same procedure will be applied here. This is based on your even parity concept, and one extra bit is going to be 8. So this one extra bit, it will be 0, it can be 1. So it's up to your design, that you are talking about even parity or you are talking about the odd parity. If you are talking about odd parity, so make your code words number of one need to be odd or even. Okay. So let's come to the next one. So this is our encoder and decoder for a simple parity check code. So again the same one, we have a sender and we have a data word, then we have a generator. Generator what can do? Generator can encode some bits. Then we have a parity bit. So this generator adds some parity bit. Parity bit, redundant bit. So redundant bit can also be known as by parity bit. So how many parity bit we need to be add here? So one parity bit, because it's a simple parity check or a single bit error detection. So in a single bit error detection mean we will add one bit. We will add one bit. So that's why we add one parity bit. So this is our code word. So now this code word is going to be transmit. The receiver will receive that code word. So will be Q0 in this form. The coming to the checker. Then the parity bit will come towards, and the code word will come towards the checker F. Set ROM is based on this one. If there is any kind of error, so it will go back and make it to be correct, then come back. But if there is no error, so it will be coming to the decision logic, and it will say okay, this is our basically a data words, and the extra bit is going to be discode. So and the receiver end we will have our correct or exact data word. So this is basically a block diagram of a simple parity check, or we can say it a single bit error detection. Okay, so this is syndrome S, which can be detect the bit that is there is any bit error or not. It will be detect your bit error. So let's come to the example 10.12. Let's look at some transmission scenario. Assume that the sender send a data word of 1001011. This is your data words, and this is our code word now, because we add just one extra bit. So let's come to the sum. So which is sent to the receiver. So we have some cases now. Initially we will say that no error occur, because you are talking about the even parity. So how many number of one will be here? 1 2 3 4, 1 2 3 4. So okay, the data would same, the syndrome will be 0, and the data would 1011 is created from this one. Then coming to another one, let's see, we will say that assume that one single bit error changes. Let's see A1. Let's see, this is our A1. Let's see, A1 is going to be changed. So A1 is going to be changed. The receiver code will be 10011. This is going to be changed now. So how many number of bits here? 1 2 3. So the syndrome is detect a 1, and no data will be created because there is a bit error, and the error is detected. Okay. Okay, coming to third one. One single bit error changes or not. The receive code word, let's see. Now this is going to be changed. The receiver code word is 10110. So again, syndrome is 1 because there is a bit error detection. So no data word is created because the code word is going to be the code word is corrupted. So that's why no data word will be created. So coming to the fourth one, an error changes or not, and a second error changes A3. Let's see, 2 bit is going to be changed, this one and this one. Okay, 2 bit is going to be changed. So what should be our code word in the receiver? And 00110. So now in this case, if you can see that number of a 1 is even, but there is a 2-bit error. So the syndrome will show that there is no bit error. There is no bit error detection, because number of a 1 are based on even parity. The code word is fine, but the data word 0011 is getting from this. So then this data word is not be in our table. So 01 is created at the receiver. Note that here the data word is wrongly created due to the syndrome value. Okay, sometimes it can be our date. So if you remember that we have a code word will always be greater than the data word, because we have a wrong code word. So we just discard the code word and receive another one. Okay, so one thing you guys need to keep in mind that whenever we have a even number of error, so the simple parity check cannot detect the error. So that's why we are saying that a simple parity check code can detect an odd number of error. So simply parity check will always be detect odd number of error. So coming to the all Hamming code discussed in this book have a d-minimum equal to 3, 2-bit error detection, and a single bit error correction, because mostly we have more than 1-bit error. So that's why d-minimum will be 3 and 2-bit error detection and 1-bit error correction. So a code will consist of n bit, which k, or a data bit, and or a check bit, so and so on. So coming to the most important scenario, once we have a 2-dimensional parity check, we study about single parity and in this slides. So now we are talking about 2-dimensional parity check code. Okay, let's see. We have this word. This is our code words. In a series or in a parallel, this is our code word. Now what we are going to do, we are going to add extra bit, or we are going to make a parity bit, or we are going to add redundant bit. So initially talking like in this way. So how many ones we have? 1 2. So we are talking about even parity. So the redundant bit will be 0, because number of a 1 is already even, so no need to add a 1. So then in this way, 1 2 3. So number of 1 is 3. So we are talking about even parity. So the redundant will be 1. So then 0 1 1 0. So we have a number of 1 is even. So the parity bit will be 0. So 1 2 3 3. So parity will be 1 0 1 it's already be even, so 0. Now we did it in a column wise, so now we did it in a period wise. So 1 2 3 4 5. So how many ones we have in the series? 5. So the parity bit will be 1, so we are talking about even, so number of 1 will be even. So then added 1, then we can add 0, then we can add 1. Okay, so then we can see here as well. So 1 2 3, so number of 1 is 3, so we need to have a even parity, so the parity bit will be 1 here. So this is called 2-dimension parity check. So you are, once you are going to send this data, so the data word will be sent in this form. It is our code word now. So this code word is going to be sent from point A to point B, and the receiver will receive this kind of a correct code words, and then that will be our message from sender to receiver. Coming to this one, once we have 1 bit error, let's see. Now this is our sender side. Let's see, this sender, both are sender side, and we have 1 bit error in the receiver end. The receiver receives this kind of a code. Let's see, this bit is going to be corrupted. This bit is corrupted. Okay, so this bit is corrupted, mean it will flip to 1. So 1 2 3 4 5, let's see, it's okay. So 1 2 3 4 5. Okay, if this bit is going to corrupt, let's see, this is 1, it's going to be 0. If it's 0, so 1 2 3 4 5, this is going to be corrupted, this code word is going to be corrupted. Then 1, this is all in, this is 1, so 1, this is 1, it means this is also be corrupted. So now 2 code word is going to be corrupted, this code word is going to be corrupted, and this is going to be corrupted. Okay, so by this way, so we can easily detect that how many code word is going to be corrupted and unused for us. Okay, so coming to this one now, once we have a 2-bit error, so let's see, this bit is going to be corrupted, and this is going to be corrupted. So now we can see 1 2 3 4. So this code word is even now, but it's not a correct code word, but according to our said ROM that we have a even parity, so it means this code word is valid but unused. But if you can see this way, that this was 1, is going to flip to 0. So how many ones we have? 1. So this code word is going to be corrupted now, and this is 1, and this is going to be corrupted. So 2 code word is not going to be used, 2 code word is going to be corrupted, and 1 is not unused. So 1 error affect 2 parities, 2 error affect 2 parities, it's the same. Okay, so one thing keep in mind again, whenever we have a 2-bit error, when we have a 2-bit error detection, so at that our said ROM cannot detect the error, because our parity will be the same. Once the parity is going to be the same, so said ROM cannot detect the error. So that's why even parity is not working in a parity check. So that's why you are saying when there is a odd number of a bit error, so the said ROM can detect the bit error. Okay, so this was about the concept of 1-bit and 2-bit error. So just keep in mind, when there is the odd parity and the result is the odd, so that code words will not be used, but the code word will be the same, because syndrome cannot detect 2-bit error. So coming to this one, let's see, we have a 3-bit error. So 3-bit error, this one is going to be corrupted, this is going to be corrupted, and this is going to be corrupted. So now see, 1 2 3 4 5, so this code is going to be corrupted, not and not be used. Or then 1 2 3, this is going to be corrupt. Then we can see this one, 1 2 3 4 5, this is going to be corrupt. Then 1 2 3, this is going to be corrupt. So now coming to this one, 1 2, so this is the this is not a corrupted code word, but will not be used because this is in even parity in this way. So it will not be used, but the syndrome cannot detect 2-bit error in a single code word. So in this case, if you can see, 3 error effect 4 parities, but there is a odd number of a parity, there is odd number of error bits, so that's why the syndrome can detect some error detection here. Okay, but coming to this one, we have 4 parity, we have 4-bit error, so 4-bit is corrupted. Then the same concept that when there is even parity, so the syndrome cannot detect the error. If you can see that 1 2 3 4 5, then if you can see 1 2 3, then you can see 1 1 2 3. So 4 error cannot be detected, syndrome cannot be detected, so up to 3 we can be detect the error. So let's come to the table. So now coming to table 10.4, Hamming code is C74. Okay, so n is equal to 4 and k is equal to n is equal to 7 and k is equal to 4. So how many extra bit we need to be had here? 3. So this is our data word and we have a code word, so how many extra bit we need to be at? 3. So it's up to you now to make your code to be even. So 3-bit, it can be 0 1 1, it can be 0 0 0, it can be 1 0 1, but it depend on your even parity. So make your code words in a even parity. If you can take it as odd parities, you can be take it, but I'm just talking about even parity, so I'm making an even parity. Let's see, this is 1, so I need even, so I think so this is 1 2 3, so this is an odd parity. In here we are talking about odd parity, so make it odd. So this is how many 1, so 1 2 1 2 3 1 2 3 4, then 1 2 3 4. So we have a number of a code word here, and so how many code we have? 1 2 3 4 5 6 7 8 8 8 16. So let's see, we have a 16 code word. In a 16 code word we have some useful code word and we have some unuseful code word. So basically from 3 bits, from these 3 bit 2 raised to power 3, we have 8 extra code words. So maybe there will be some useful, there will be not useful. If you are talking about the even parity, so take all those code words which are in even parity, but if you are talking about in odd parity, so take all those code words which are in odd, so that will be your useful code word. But it's the total number of a code word which can be possible to make from a 3 bits. Okay, but if you take a even parity, so take it even parity from it. If you take odd parity, take odd parity code word from it. So calculating the parity bit at the transmitter, just about your module, that it can be A1 A2 and A0 or A0 A1 A2 and so on. Then it can be syndrome can be B. So just up to just simple calculating of syndrome and parity, as you can also solve it in a block diagram. So this is a block diagram, simple. Again, you have a sender, we have a data word, and data word have some encoding. We can add how many bit? 3 bit. We are adding a 3 parity bit, so 3 parity is going to be 8. So this is our code word, send this code word, but keep in mind in which format you are sending, in odd parity or in even parity. If you are going to be talking about the odd parity, so odd parity will be known here and odd parity will be known here. Okay, but if you're talking about even parity, so even parity will be known here, even parity will be known here. So that will be, this is called synchronization, that each and everything will be the same in the sender and receiver side. So this code is received here, so checker will check that and will check the syndrome. If there is any bit error, so it can be bounce back, and if there is no bit error, so your coder will be the same here, and this is your receiver code data word, because code word. So the checker will remove the parity and the data word will be received here. This is a block diagram about the encoder and decoder of Hamming codes. Okay, so try to solve this example by yourself. This is the same method, same concept will be applied here. Okay, and again this one again the same as well. So this is your homework, so try to solve it out, but if you have any questions, so you can be asked. Now coming to the burst error. So burst error are very common, in particular in a wireless environment where a fade will affect a group of a bit in a transit. The length of the burst depends on the duration of the fade. One way to counter burst error is to break up a transmission into a shorter words and create a block, one word per row, then have a parity check per word. The words are then signed column by column. When burst error occur, it will affect one bit in the serial word as the transmission is read back into the block format and each word is checked individually. So burst error means we have more than one bit error, that's called burst error. So burst error, so how we can detect the burst error and how we can correct the burst error, for that we have a method. So same Hamming distance we can be used for error detection, and so now simple parity check will not be used here. So look at the burst error correction using Hamming code diagram. So let's see, we have a code word 1 2 3 4. This is code word. So what we are going to do, so we are sending the data in a column wise. So initially what we are going to do, 1 is going to be sent, 0 is going to be sent, 0 is going to be sent, 1 is then this one is going to be sent, then this one, this one, this one. So parallel we are going to our column wise, we are sending our bits now. So we are sending this 1 0 1 1 1 1 0 1 1 1, then we have 1 1 0 0, then we have, so this is our basically total data of a code words, data of 4 code words. So in a transmission medium we are transmitting these code words from sender to receiver. So through in a transmission medium, so how many bits is going to be corrupted now? 1 2 3 4. So 4 bit is going to be corrupted. It means this is a burst error now. So this is more than one bit error, so this is a burst error. So this data, this code is going to be received towards the receiver end. So you can see again it will be received this one, receive this one, because it's a parallel, or we can say column wise. Then what? So if you can see how many bits is going to be changed, so this bit there is 0, there was 1, so this is going to be changed, then is a 1, there is a 0, this is going to be changed, then this is going to be changed, and this is going, so 4 bit is corrupted here. So using a Hamming code, so we can correct this kind of error as well. So just keep in mind this kind of scenario in your mind. So in the next lecture I will tell you that how we can correct 1 bit error, how we can correct 2 bit error, how we can connect 3 bit, 4 bit, and so on. Okay, so we have a method for that. So this is like a burst error correction using a Hamming code. So how we can so simply, if you can see both sides, okay, this is 0, this one, okay, flip out. But for that we have a method that which bit is going to be corrupted. So how we can find that which bit was corrupted and which bit was need to be flip out now. If it was 0 in the sender side, but in the receiver it is 1 now, so just flip it from 0 to 1 or 1 to 0 to make your code word to be correct. Okay, so this we have a method for it, so later on I will show you. So this was about your burst error. So you guys can be watch the video and hope it will help you. If you have any question, kindly raise your question, I will try to answer it. Thank you for your time. See you in the next lecture.